All right. All right. So the last thing that I wanted to do from improper integrals is this comparison theorem. The idea of comparison theorem is that suppose that you know certain improper integrals are convergent or divergent. Can you use information about some known improper integrals to decide whether some other improper integrals are convergent or divergent? Is that clear? Can I understand whether some improper integrals are convergent or divergent based on my knowledge that some other integrals are convergent or divergent? And so what I'm going to do is I'm going to pick two functions here. So let's say 0 is less than or equal to g of x, is less than or equal to f of x, and I am going to assume that x is these inequalities. There are two inequalities here, right? These inequalities. So these inequalities are telling me that f and g are both non-negative, and also it's telling me that f is larger than g, right? In terms of the graph of f, what is it telling me? The graph of f is above the graph of g, right? And both of the graphs would be above the x-axis. Now, notice I'm going to say that these inequalities hold for any x between star and double star. I don't want to write down anything for star and double star. Star and double star could be numbers, could be infinity, could be negative infinity. Am I making sense? Now we are going to look at, now consider two integrals, okay? Integral from star to double star. So basically star is my lower limit, double star is my upper limit. Look at the integral of f of x dx. Let me call that integral number 1. Integral number 2 would be the integral from star to double star of g of x dx. And they are improper integrals, okay? These are improper integrals. Okay, either of type 1 or type 2. Now, it is key that both of them are non-negative. So what I'm going to say now wouldn't hold if they are not non-negative. Okay. All right. So what I want to say now, one thing to realize here is that I said the inequalities 0 less than g less than f hold for any x between star and double star. I didn't say they hold when x is equal to star or x is equal to double star, right? I didn't say anything about what happens when x is equal to star or double star for the inequality, right? Didn't say anything. But when x is between them, then I said those inequalities hold. Now, can someone tell me, or can someone answer the following question? Suppose that I know improper integral number 1 is convergent. What does it tell me about integral number 2? If I know, very good. So if I know integral number 1, if I know integral number 1 is convergent, then I know that integral number 2 will be convergent. Why? Because g is smaller than f. Now think about the graph. Integral of g, let's say f and g, so between star and double star, I don't know what's happening at the limits of integration, but in between them, let's say they are continuous functions. Then look at the graph of g, right? Look at the graph of g. The integral represents the area below the graph, right? So integral of f is higher, f is above g, right? So integral of f is convergent says what? The area below f is finite. Well, then the area below g has to be finite, so the integral of g has to be convergent, right? Now let's think about the other way. What if I tell you that integral number 2 is divergent? Here is g, here is f. Number 2 is divergent, integral of g is divergent, means the area below g is infinite. Well, then the area below f is definitely infinite, right? So that means if number 2 is divergent, then I can say number 1 is divergent, right? So that's all. That's the comparison theorem, really. So the comparison theorem says if 1 is convergent, then 2 is convergent. Okay? If 2 is divergent, then 1 is divergent. Now let me ask you this. What if 1 is divergent? What can I say about 2? You don't know, actually. Very good. Very good answer. And also remember that f and g both have to be non-negative. Otherwise, whatever we are saying is going to be wrong. Why? I mean, think about this. Suppose that you know that the integral of f is convergent. F is positive. However, let's say g is not positive, but g maybe have arbitrarily large negative values, right? Then this, whatever we are saying, may not work. Okay? So it's important that both of them are non-negative. Both integrands are non-negative in order to compare them. Is that okay? Let's look at examples to see how we could use comparison theorems to decide whether certain integrals are convergent or divergent. But let me remind you something. Integral from 1 to infinity 1 over x to the p dx. This is convergent when p is what? Larger than 1. And it is divergent when p is less than or equal to 1. Right? We discussed that in our previous lecture. Everybody is okay with that? What if I go from negative infinity to negative 1 instead of going from 1 to infinity? What if I go from negative infinity to negative 1? Do you think the result is still true? What did you say? Well, why don't you think about it and see if you can come up with what the answer is. All right, so we're going to just use this in a second. So here's an example. Let's say I have the integral from 1 up to infinity 1 over the root of x cubed plus 5 dx. That's all. The question is not to evaluate. The question is it convergent or is it divergent? That's all we want to know. We don't care about the value. We want to know if it is convergent or divergent. That's all we want to know. Now, can someone tell me your feelings about this integral? Do you think it should be convergent? Do you think it should be divergent? You are thinking that it should be convergent. Why? Yeah, so what he's saying, we are looking at an infinite interval from 1 to infinity, and in the denominator I have pretty much x cubed, right? Root of x cubed, if you ignore that 5. Well, 1 over root of x cubed, what is that? 1 over x to the 3/2. And the integral of 1 over x to the 3/2 is convergent, as we saw in terms of p, right? If p is bigger than 1, it's convergent, right? So that tells me it should be. But how do I use my comparison theorem to justify that it is convergent? So now that I feel that it should be convergent, what should I do? Well, I should try to show that my integrand is smaller than 1 over x to the 3/2, right? If I could show that, then my comparison theorem tells me because the integral of the right hand side is convergent, the integral of the left hand side will be convergent, right? But how do I establish this inequality? Is everybody clear? It's because I want to show that my integral is convergent, I need to come up with an upper bound function and show that the integral of the upper bound function is convergent. Right? I want to show my integral is convergent, then I have to come up with an upper bound function that is convergent. Well, how do I do that? Well, as you said, would you agree that this integrand that I have is smaller than this? Is it clear that it's smaller? Why? Which denominator is bigger? Both numerators are the same. Same numerators. Which denominator is bigger? On the left hand side. So which fraction is smaller? The left hand side, right? So but what is that? That is exactly 1 over x to the 3/2. And these inequalities hold for what? For any x larger than 0 it works, right? In fact. And for any x larger than 0 it works, but I don't really need that. All I need that it is definitely works. It definitely works when x is larger than 1. Well, since the integral from 1 to infinity 1 over x to the 3/2 dx is convergent, we have that our integral is also convergent. By the comparison theorem. Is everybody okay with that example? You guys have any questions on that example? Everybody's okay? All right. Another example. Let's say I have the integral from 1 up to infinity sine of x plus 3 divided by root x dx. All right, same question, convergent or divergent? How do you feel? Divergent why? Very good, very good. Because my numerator is a bad looking function, but we are looking at the interval from 1 to infinity. However, the numerator is always bounded, right? At most 4 or at least 3, right? But my denominator is root x. So basically the whole quantity is dominated by that root x, right? So I almost have 1 over root x, right? So that tells me that because the integral of 1 over root x is divergent, that my integral should be divergent, right? You agree? So that means I want to show this integral is divergent. If I want to show that my integral is divergent, then what do I have to do? Well, I have to come up with a lower bound function. Remember, if I want to show my integral is convergent, I had to come up with an upper bound function that is convergent. If I want to show my integral is divergent, then I have to come up with a lower bound function and show that the lower bound is divergent. So that means I have to show this is bigger than or equal to 1 over root x, right? That's what I want to accomplish. I want to accomplish that my integrand is bigger than 1 over root x, okay, in some infinite interval. Well, why is that the case? Let's see. Sine x plus 3. You just said sine x is between -1 and 1. The largest value of sine is 4. The smallest value of sine is -1. What can I say about the numerator? Can you tell me what's the smallest value of the numerator? The smallest value of the numerator is 2, right? When sine is -1, you get 2. So the smallest possible value of the numerator is exactly 2. Which tells me I have basically 2 over. I have at least 2 over root x, right? Well, definitely it is greater than. So I should say greater than 2 over root x, which is obviously greater than 1 over root x, right? And this is true for any x bigger than 1. In fact, it's true for any x larger than 0, right? But that will do. Again, why? Because since the numerator sine x plus 3 is at least 2 for all x. For all x, it is at least 2. The upside down a means for all. So for all x, the numerator is at least 2. So I know that those inequalities are true. So then what? Well, since the integral from 1 to infinity 1 over root x dx is divergent by the comparison theorem, our given integral sine x plus 3 over root x dx is divergent as well. Is everybody okay? Well, now let's look at 2 more examples on this, which will be similar to your homework questions. I want to point out one thing here. In your homework, you might see certain integrands involving the exponential or the log function, right? You shouldn't think about, oh, I don't know how to work with that, because in those problems, you're not asked to evaluate those integrals. You're asked to decide whether the integral is proper or improper, right? Which can be decided without knowing too much about those functions. Let me just say one thing. Exponential functions are continuous everywhere. The log function is continuous from 0 to infinity, excluding 0. Okay, if you know that, you don't need to know anything else. The exponential functions are continuous everywhere. The log function is continuous from 0 to infinity, excluding 0. And that's all you need in your homework. Okay. Let's see. I wanted to do a problem where you have to use the comparison theorem. Let me see if I can find. Where is that? Am I missing? Actually, let me find it out from what I did in the morning. Okay, x plus 1 over x cubed plus 5. Okay. Let's say I have x plus 1 over x cubed plus 5. And let's say the integral goes from 0 to infinity. Okay. Again, the question is not to evaluate. The question is it convergent or divergent? Is everybody okay? Of course, if you know how to evaluate it, you will know whether it's convergent or divergent. But if you try this problem, try to evaluate, you probably will get into trouble. You won't be able to do it. So is it convergent or divergent? We're going to apply the comparison theorem. What is my intuition telling me? My intuition is telling me that this is why? If you ignore 1 and 5, you get 1 over x squared, and the integral of 1 over x squared from 1 to infinity is convergent, right? Right? So that tells me, but there is a little bit of confusion about what's happening between 0 and 1. Right? So, first of all, let me tell you that, okay, this is greater than, not greater than, sorry. Let me say that this is less than or equal to x plus 1 over x cubed. Why? Same numerators. The denominator on the left is bigger. Right? That's why. And then, can I say that this is less than or equal to x over x cubed? Is that true? Think again. Is x plus 1, same denominators, x plus 1, is it less than x? No. So I can't really say that, but I want to get there. I want to get 1 over x squared. So what should I do? Well, okay, x plus 1 is not less than x, but I can say x plus x is greater, x plus x I can say is greater than x plus 1, but as long as what? As long as I assume that x is at least 1. Right? As long as I assume x is at least 1, then x plus x is bigger than x plus 1. Right? Well, then what do I have? I have x plus 1 over x cubed plus 5 is less than or equal to 2x over x cubed. And so x plus 1 over x cubed plus 5 is less than or equal to 2 times 1 over x squared, and this is for any x larger than 1. Okay? So now, note the integral from 1 up to infinity of 2 times 1 over x squared dx is the same as 2 times the integral from 1 to infinity 1 over x squared dx is convergent, right? This is convergent. This is convergent. So what can I say? What can I say about x plus 1 over x cubed plus 5? So, by the comparison theorem, integral from 1 to infinity x plus 1 over x cubed plus 5 dx is convergent. Is that right? Is that right? Because what did we say? We said this. We said that x plus 1 divided by x cubed plus 5 is less than 2 over x squared, but it only works for x bigger than 1. So because the upper bound is convergent from 1 to infinity, the lower bound will be convergent from 1 to infinity. But have I answered my question yet, though? Well, my original integral was what? Was from 0 to infinity, right? My original integral was from 0 to infinity, not 1 to infinity, right? So what can I say now? So now that I know this, so let's look at the integral from 0 to infinity x plus 1 over x cubed plus 5 dx. Well, notice this is the integral from 0 to 1 x plus 1 over x cubed plus 5 dx plus 1 to infinity x plus 1 over x cubed plus 5 dx. What have we accomplished? We said this is convergent by using the comparison test. What about this guy? Is that improper? Is that improper? No, it's not improper, right? The integrand is continuous between 0 and 1. It's not improper. If it is not improper, then it's already defined, right? It's a continuous everywhere between 0 and 1. So this is a number, right? This is some number, whatever that is, some number. This is some number. Right? So together, is it convergent or not? Yes, together it's convergent. Right? So convergent. That makes sense. Any questions on that? I'll be doing one more. Okay, let's see if you do that. Do I need to go up for you to see the previous work? Everybody is okay? All right.
What was your thinking? Why were you trying to get 1 over x squared?
Because I looked at my integrand, right? X plus 1 over x cubed plus 5. And I immediately think that this is almost the function x over x cubed. which is almost like 1 over x, which is the same as 1 over x squared. So that made me assume that my integral should be convergent. Right? So then if I want to show that this integral should be convergent, then my goal should be to show that my integrand is smaller than 1 over x squared for some infinite interval. It doesn't have to be from 0 to infinity. It has to be from some number to infinity. Okay? You don't have to show that it's less than 1 over x squared from 0. Okay? From some number to infinity. And then you worry about what's happening between 0 and 1 or 0 or 2 later. Okay? So I got 1 over x squared because I thought about 1 over x squared. I looked at the integrand and I say that the integrand is almost like 1 over x squared, so it should be convergent, and my goal should be to show that my integrand is smaller than 1 over x squared, and because 1 over x squared the integral of 1 over x squared from 1 to infinity is convergent, the integral of my integrand from 1 to infinity will also be convergent. And then I'm going to worry about what's happening between 0 and 1. Is that okay? Now, these things are a little bit different than what you are usually used to when solving problems, right? Inequalities are usually a little bit tedious than most other problems. But there is a reason why I am usually sometimes we don't emphasize the comparison theorem. But the reason I am emphasizing the comparison theorem is that there is an entire chapter on what is called series, okay, series and sequences. And when we get there, it's going to be all about inequalities, okay. And so maybe this is a good practice for us to start dealing with inequalities, and when we get there, we will feel a little bit better. Okay, so here's my last example on improper integrals. Let's say I have the integral from 1 up to infinity. Let's say I have x minus 1 over... You know what? Let me change it a little bit. Okay, let's just say x minus 2. And then I have the root of x to the 4 plus x dx. Okay, I have that integral. And I actually made it a little bit harder than what you have in the homework, but very, very similar. In the homework, instead of having x minus 2, you have x plus 1. And in the denominator, instead of having actually 4 plus x, you have... you know what? And let me not change the denominator because I actually made it easier to think about, okay? So let's just have negative again. So that's the same denominator you have in the homework. Now, how would I do this? Well, once again, let's try to get some intuition. This is almost x over root of x to the 4. Root of x to the 4 is... why? Because we are going from 1 to infinity. So when x is large, you see the convergence doesn't depend on a finite interval. It depends on what's happening up there. Okay, when you have an infinite interval, the convergence depends on what's happening in the extreme side, and so I can say that x to the 4 is much bigger than x. Like after, let's say, x is 100. Once you go above x equals to 100, think about the x to the 4 and x. X to the 4, 100 to the power 4 is way bigger than just 100. Okay? So I can ignore that x. I can only look at x to the 4, and then this integrand is like x over root of x to the 4, which is what? X divided by root of x to the 4 is x divided by x squared, which is 1 over x. What do we know about 1 over x? integral from 1 to infinity of 1 over x is, yeah, but it's divergent or convergent? Divergent. Remember, if p is, remember what we said here. If p is less than or equal to 1, integral from 1 to infinity of 1 over x to the p is divergent. You're right. You use the log function to evaluate and see that's the case. Okay. All right. So let's get there. So then, if I, so what do I want to show? I want to show that my integral is what? I want to show my integral is divergent, right? Because I think it is almost like 1 over x. If I want to show my integral is divergent, what do I want to show? Do I want to show that it's bigger than 1 over x or less than 1 over x? Bigger than, because I want to show that it's bigger than 1 over x, and because 1 over x is divergent, the bigger one should be divergent as well, right? So I want to show this is bigger than 1 over x, right? Let's see if we can accomplish that. Well, first of all, let's do the following. Can I say this? Which denominator is smaller? On the left, right? Smaller. So this is a correct inequality. But this is as long as what? As long as here, let's say x is larger than 1, right? X is larger than 1. You agree? When x is 0, the left-hand side is undefined, right? All right. What can I say then about the next? So I want to get to x, right? So how can I introduce just x in the numerator? How would you introduce just x? I cannot say this is bigger than x, can I? I can't say that it's bigger than x, right? Then you're making 2x here, right? So instead of saying that, let's just say this is bigger than or equal to x minus x over 2. Okay? Which means that I am trying to subtract more, right? If I want x minus 2 to be bigger, then I have to subtract more from x, right? Which means I want this guy to be what? I want this guy to be larger than 2, right? Which means I need x to be what? I need x to be larger than, so I need x to be larger than 4 if I want to go there. And then I can say this is a half x over x squared, which is 1/2 times 1 over x. Did that last step make sense? You're going from x minus 2. You want to have just x. Now, you are subtracting 2 from x, right? So, in order to make it bigger, in order to get something smaller, you have to subtract something bigger than 2. Okay? If you subtract something bigger than 2, so I want this guy to be bigger than 2, which means that x is bigger than 4. So when x is bigger than 4, x over 2 is bigger than 2. So I'm subtracting something bigger, so I could say that. And now in your homework, it's actually easier, because in your homework, instead of x minus 2, you have x plus. So if I have x plus 2, going from here to here is what? Easy, because you can just say x plus 2 is bigger than x. Right? You agree? If I had x plus 2, I didn't need any of this mumbo jumbo here. Right? If I had x plus 2, all I can say x plus 2 is bigger than x, right? and I don't need to restrict x anymore. So that's what I have. So at the end I have x minus 2 over root of x to the 4 minus x, right, is larger than or equal to half 1 over x, and this is as long as x is larger than 4. Okay, or larger or equal to, I could say. Okay, so now we are going to use that. Okay, so the integral from 4 to infinity x minus 2 over x to the 4 minus x dx would be larger than the integral from 4 to infinity half 1 over x dx, which is equal to half outside integral from 4 to infinity 1 over x dx. Is that divergent from 4 to infinity of 1 over x? You might say, hey, you said 1 to infinity of 1 over x is divergent. How does that imply that 4 to infinity is divergent as well? Well, if you don't believe me, you can compute that in terms of the log function and see that that's the case. What I'm saying, if I know that the integral from 1 to infinity is divergent, then I know that the integral from 100 to infinity is divergent. 1000 to infinity is divergent. Meaning is, it doesn't matter what's happening initially on a finite interval. What it matters is what's happening in a infinite interval from some point on. Okay? So if you know that the integral from 1 to infinity of some function is divergent, then you also know that integral from 10 to infinity is also divergent. Okay? The convergence divergence does not depend on the initial on a finite interval. It's not determined by a finite interval. Does that make sense? So between 4 and 10, between 1 and 4, what happened doesn't matter. What happens is that convergence depends on what's happening at the end. Is that okay? So 4 to infinity is divergent. This is divergent. This is divergent. Well, that shows that my integral 4 to infinity is divergent. So, but what did I want to decide though? Did I want to decide the integral from 4 to infinity of x minus 2 over root of x to the 4 minus x dx? No, I had what? I had 1 to infinity, right? I had 1 to infinity. Do I have to worry about what's happening between 1 and 4? It's divergent, right? If it was convergent, then I have to worry about what's happening between 1 and 4 to see if it is convergent. But I already have 4 to infinity is divergent, so who cares what's happening from 1 to 4? Am I making sense? So again, our original integral is from 1 to infinity x minus 2 over x to the 4 minus x root of that dx. Even worse, our integrand is actually discontinuous at the lower limit, right? Right? It's blowing up to infinity at that lower limit 1. Now, this is equal to 1 to 4 plus 4 to infinity, and we said that this is divergent, right? And then what I'm saying, doesn't matter what happens at between 1 and 4, it's still divergent. So this is divergent. You're okay with that? It's still divergent. As long as once you break it up, if one of the terms is divergent, then the other is. Okay. Anything else? Anyone has any questions? Okay, keep looking at these examples and do the problems in the homework. I guess you sort of know what the answers are for your two of your homework problems, because I did very similar problems and the answers are pretty much the same for the homework problems. But you should go over it and try to follow the same steps and arguments that I gave and see if you can do that, okay? All right.